reporting mathematics in 17th century. This century came to be known as the age of scientific revolution. People began to accept Aristotle's view of the universe, and the scientific method or process were emphasized. The foundations of modern science were laid as more and more of them began to discard the medieval teachings and clinch new views of the universe. Persecution of those who opposed medieval teaching stopped as scholars enlightened people using of science. Century, this period was also one of the intense activities and innovation in mathematics. Advances in numerical calculation and development of symbolic algebra and analytic geometry, and the invention of differential and integral calculus resulted in a major expansion of the subject areas of mathematics. Mathematics teaching in the 17th century. Science has immensely benefited due to the discovery of new ideas in mathematicians. Mathematics attempted to explain the nature of the universe mathematically. Education became important in the curriculum as advances in the science continue unabated. Mathematics scholars studied mathematics in its pure form, while others used mathematics as advanced concept in science or apply mathematics in inventing machines. Now, we will proceed to the mathematicians in the 17th century. First, we have René Descartes or René Descartes. René Descartes was a French-born Dutch philosopher, mathematician, and scientist. A native of Kingdom of France, he spent about 20 years of his life in Dutch Republic after serving for a while in the Dutch States Army of Maurice of Nassau, Prince of Orange, and the Stadtholder of the United Provinces. He was born on March 31, 1596 in Descartes, France, and died on February 11, 1650 in Stockholm, Sweden. And he was studied in the University of Poitiers, influenced by Plato, Aristotle, and Augustine of Hippo. He has a child named Francine Descartes. René Descartes in 17th century. First, he wrote a book about the unification of algebra and geometry. Then, Descartes' rule of sign, known in his discovery the rule of signs which is commonly used in modern mathematics. Then, the classification of curves. This was the first classification of curves according to the types of equations. And he was honored by having the Cartesian coordinate system. I have a video about René Descartes and his contribution in mathematics in 17th century. Let's watch this.
René Descartes, father of modern philosophy, one of the key figures in the scientific revolution of the 17th century, and one of the first of the modern school of mathematics who laid many of the foundations for calculus and algebra. He was born on the 31st of March, 1596, in a small French town. As a young man, he was a mercenary for many countries, both Protestant and Catholic alike. But after meeting with the Dutch scientist and philosopher Isaac Beeckman, who gave him his interest in mathematics and new physics, he came to the decision that his real destiny in life was to pursue true wisdom and science. Back in France, the young Descartes soon realized that the key to philosophy, with all its vagueness, was to build the foundations on the unchangeable facts of math. To realize his heretical ideas, furthermore, he moved from the highly conservative Catholic France to a more liberal society in the Netherlands, in which Descartes would spend the majority of his adult life and where he achieved the goals of merging geometry and algebra. In the year 1637, he published his mathematical and philosophical book called Discours de la Méthode, or Discourse on Method. One part of the book in particular, La Géométrie, is today seen as a huge step forward in the history of math. Going after early movements, seeking to use symbols and expressions in mathematics, La Géométrie gave us what has become widely known as the standard for algebraic notation, which uses lowercase a, b, and c for known values and x, y, and z for unknown values. It was the first book that could resemble a modern algebra textbook, using symbols we know and love today. Cartesian coordinates. In La Géométrie, Descartes first claimed that every point in 2 dimensions can be interpreted by 2 numbers on a plane, with one value giving the point's horizontal location and another value the vertical location. This has become known today as Cartesian coordinates, a huge staple in modern math. He used perpendicular lines, or axes, crossing at a point called the origin, to measure the horizontal x and vertical y locations, both having positive and negative values, therefore dividing the plane into 4 quadrants. An equation can be visualized on the plane by plotting on it the solution set of the equation. For example, the simple equation y equals x yields a straight line connecting together the points 0, 0, 1, 1, 2, 2, etc. The equation y equals 2x gives us a line with steeper slope connecting points 0, 0, 1, 2, 2, 4, etc. More complex equations involving x2, x3, etc. plot many different types of curves on the plane.
Descartes' earth-shattering work allowed for the conversion of geometry into algebra, and vice versa. With it, a pair of equations could now be solved either geometrically or algebraically. This allowed for the development of Newton's and Leibniz's discoveries of calculus later on. It also gave us the possibility of working with geometries of higher dimensions, impossible to visualize physically, an idea which has become crucial to modern physics and technology, which changed mathematics forever. Descartes' rule of signs. Analytic geometry was far from Descartes' most crucial addition to mathematics. He also created a rule of signs method for finding the number of positive or negative real roots of a polynomial, popularized a superscript notation for showing powers or exponents, for example 24 to show 2 times 2 times 2 times 2, and reinvented Thabit ibn Qura's formula for amicable numbers. Despite all his influence in the creation of modern mathematics, Descartes is best known today as a philosopher who advocated dualism and rationalism. His philosophy was made up of a method of doubting everything, then reforging knowledge from the ground up, and he's especially well known for the famous statement, cogito ergo sum, or I think, therefore I am. Descartes also played a role in the advancement of modern physics, a role that's been generally underappreciated until very recently. He gave us the first modern system of laws of nature and the conservation principle of motion, made many advancements in optics and the study of refraction and reflection of light, and created the most popular theory of planetary motion of the late 1600s. His contributions to the scientific method was faced with heavy opposition by the Catholic officials of the time. His game-changing ideas made him a very controversial figure, and he died in Sweden in 1650, with many of his works being prohibited by the Catholic Church later on. It was only until relatively recently that his genius was truly known to the world. Without his contribution to mathematics, much of what we learn about algebra and geometry in Miss Clyde's class would be wildly different, and we wouldn't have as great of an understanding of such fascinating knowledge. We felt like diving into the history of math would give us a better understanding of how modern mathematics came to be, and also give us some insight to just what pre-calc might look like next year. History felt like it would be a fun thing to explore and research, and that it could be taught easily in a video.
We'll proceed to the second mathematician in 17th century. His name is Bonaventura Francisco Cavaliere. He was an Italian mathematician and a Jesuit. He is known for his work on problems of optics and motion, work on indivisibles and precursors of infinitesimal calculus, and the introduction of logarithms to Italy. He was born on 1598 in Milan, Italy. Died on November 30, 1647 in Bologna, Italy, and he studied at the University of Pisa, and he is also known as Bonaventura Cavalieros, and his field was mathematics. He is also responsible for introducing logarithms as a computational tool in Italy. Published Logarithms of Trigonometric Function for use by astronomers. Wrote on conic section, trigonometry, optics, astronomy, and astrology. Also have here a short video of Francisco Cavaliere's life and his contribution in mathematics in 17th century. Let's watch this.
Bonaventura Francesco Cavalieri was an Italian mathematician and a Jesuit. He is known for his work on the problems of optics and motion, work on indivisibles, the precursors of infinitesimal calculus, and the introduction of logarithms to Italy. Cavalieri's principle in geometry partially anticipated integral calculus. Life. Born in Milan, Cavalieri studied theology in the monastery of San Gerolamo in Milan and geometry at the University of Pisa as a member of the Jesuits order. He published 11 books, his first being published in 1632. He worked on the problems of optics and motion. His astronomical and astrological work remained marginal to these main interests, though his last book, Trattato della Ruota Planetaria Perpetuae, was dedicated to the former. He was introduced to Galileo Galilei through academic and ecclesiastical contacts. Galileo exerted a strong influence on Cavalieri, encouraging him to work on his new method and suggesting fruitful ideas. And Cavalieri would write at least 112 letters to Galileo. Galileo said of Cavalieri, "Few, if any, since Archimedes, have delved as far and as deep into the science of geometry." He also benefited from the patronage of Cesare Marsili. Cavalieri's first book was Lo specchio a storia ovvero Trattato del sezioni coniche, or The Burning Mirror, or a treatise on conic sections. In this book he developed the theory of mirrors shaped into parabolas, hyperbolas, and ellipses, and various combinations of these mirrors. The work was purely theoretical since the needed mirrors could not be constructed with the technologies of the time, a limitation well understood by Cavalieri. Inspired by earlier work by Galileo, Cavalieri developed a new geometrical approach called the method of indivisibles to calculus and published a treatise on the topic, Geometria Indivisibilibus Continuorum Nova Quadam Rationa Promota. In this work, an area is considered as constituted by an indefinite number of parallel segments and a volume as constituted by an indefinite number of parallel, planar areas. Such elements are called indivisibles respectively of area and volume and provide the building blocks of Cavalieri's method. As an application, he computed the areas under the curves, an early integral, which is known as Cavalieri's quadrature formula. Cavalieri is known for Cavalieri's principle, which states that the volumes of two objects are equal if the areas of their corresponding cross-sections are in all cases equal. Two cross-sections correspond if they are intersections of the body with planes equidistant from a chosen baseplane. Of China, Cavalieri developed the method of indivisibles which he used to determine areas and volumes. It was a significant step on the way to modern infinitesimal calculus. Cavalieri also constructed a hydraulic pump for his monastery and published tables of logarithms, emphasizing their practical use in the fields of astronomy and geography. He died at Bologna. Legacy. According to Giles Gaston Granger, Cavalieri belongs with Newton, Leibniz, Pascal, Wallis and Maclaurin as one of those who in the 17th and 18th centuries redefined the mathematical object. The lunar crater Cavallarius is named for Cavalieri. Bibliography. Eloge di Galileo Galilei di Bonaventura Cavalieri by Giuseppe Galeazzi, Milan, 1778. Bonaventura Cavalieri by Antonio Favaro, Volume 31 of Amici e Corrispondente di Galileo Galilei, Ferrari, 1915, 767 p.
Proceed to the third mathematician in 17th century. He is Pierre de Fermat. Pierre de Fermat was a French lawyer at the Parliament of Toulouse, France, and a mathematician who is given credit for early development that led to infinitesimal calculus, including his technique of inequality. He was born on 1607 in Bermond de la Monnaie, France, and died on January 12, 1665 at Castres, France, and studied at University of Orleans in 1623 to 1626. He has a wife named Louise Long Fermat. His field was mathematics and law. He was influenced by Diophantus, François Vissey, and Gerolamo Cardano. And we will proceed to the contribution of Pierre de Fermat in mathematics in 17th century. He published a book containing a method for determining maxima and minima and tangents to curve lines. And also, best remember for his work in the number theory, Fermat's last theorem. And he set up the theory of probability together with Blaise Pascal. And pose further problems like sum of two cubes cannot be a cube, or a special case of Fermat's last theorem, which may indicate that by this time Fermat realized that this proof of the general result was incorrect. And also, I prepared a short video of Pierre de Fermat and his contribution in mathematics in 17th century. So let's watch this.
Most math subjects are relatively young. While geometry and arithmetic have been studied for thousands of years, other subjects such as calculus, probability, and analytic geometry were developed more recently. If you could travel back in time to the beginning of the 17th century, you would find the math collections in libraries to be considerably smaller. This was all about to change, and one of the people who helped change things was not a mathematician. Pierre de Fermat was born a little after 1600 in Beaumont de Lomagne in southern France. He received his law degree from the University of Orleans, and his professional resume was simple. He served as a lawyer and member of parliament in Toulouse until his death. And though he studied law, his education was broad. For example, he knew multiple languages including Spanish, Italian, Latin, and Greek. Fermat's knowledge of languages and mathematics was critical to one of his interests, the restoration of ancient books. One of his reconstructions was the ancient book Plain Loci by Apollonius. But Fermat did not stop there. Perhaps inspired by the work of Apollonius, Fermat went on to discover analytic geometry. Fermat also solved several basic calculus problems. He developed a way to find the maxima and minima of certain functions, and was even able to compute the area under some basic curves. At first, this may not sound impressive. These are elementary issues to students of calculus today. But remember this, calculus did not exist during Fermat's lifetime. But of all the branches of mathematics Fermat investigated, he left his greatest mark on number theory. The study of numbers, pure and simple. Number theory is one of the oldest areas of mathematics. For over 2,000 years, people have studied the basic properties of numbers. But Fermat is considered the father of modern number theory. One problem frequently asked in number theory is, given an equation, find all integer solutions. Oddly enough, the question of describing all real number solutions is relatively simple. Just graph the equation. But when you restrict the types of numbers to integers, the problem becomes much more complex. These types of equations are called Diophantine equations in honor of the ancient Greek mathematician Diophantus, and are amongst the most difficult of math problems. Coincidentally, it was while reading a book by Diophantus that Fermat made an exciting discovery. He claimed that the equation x to the n plus y to the n equals z to the n had no positive integer solutions if n was greater than 2. There are infinitely many solutions when n equals 1 or n equals 2, but for n greater than 2, Fermat was certain there was no positive solution. He made a note in his book that he had found a truly marvelous proof, but the margin was too narrow to write it down. This problem became known as Fermat's last theorem because of all his unproven statements. This was the very last one to be proven true. For over 300 years, mathematicians worked on this problem before it was finally proven by Andrew Wiles in 1994. Tremendous amounts of new mathematics were developed on the road to proving Fermat's last theorem. Given how difficult the problem was, many people wonder, did Fermat really have a proof? Was he so clever as to see a solution which no one else could see? We don't know. If only the margin had been wider.
Good day, everyone. I am Madel and I am continuing the report of Ma'am Lacandola about the 17th century mathematician. Blaise Pascal was born on June 19, 1623 in Clermont-Ferrand, France. He died on August 19, 1662 in Paris. He was a French mathematician, physicist, religious philosopher, and master of prose. He taught the experience of God through the heart rather than through reason. Pascal's father, Etienne Pascal, was presiding judge of the tax court at Clermont-Ferrand. His mother died in 1626 and in 1631 the family moved in Paris. Etienne, who was respected as a mathematician. Here are some contributions of Blaise Pascal. At the age of 12, he discovered that the sum of the angles of the triangle are two right angles. He also presented a single piece of paper to the one of Mercin's meetings in June 1639, which contains a number of projective geometric theorems, including Pascal's mystic hexagon at the age of 16. He also invented the first digital calculator, called Pascaline calculator, to help his father with his work in collecting tax between 1642 and 1645. He also the second person to invent a mechanical calculator because Chickard was the first in 1624. Please watch this video about Pascal's triangles.
This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam triangle, and in China, it's Yang Wei's triangle. To much of the Western world, it's known as Pascal's triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row and you'll get successive powers of 2. Or in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting. All ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art, it's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row, so 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5, and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics. And it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Though not the first to study the Pascal triangle, his works on the topic and treatise on the arithmetical triangle was the most important on this topic. And through the work of Wallis, Pascal works on the binomial coefficients to lead Newton to his discovery of the general binomial theorem of 4 fractional and negative powers. He also applied Cavalier's calculus of indivisibles to the problem of area of any segments of the cycloid and center of gravity of any segment. He solved problems of the volume of the surface area of the solid and revolutions formed by rotating the cycloid. The next mathematician is Christian Huygens, 1629 to 1695. He was born on April 14, 1629 in The Hague, Netherlands, and died on July 8, 1695. His nationality is Dutch. His field is physics, mathematics, and astronomy. It was through him that Christian was to gain access to the top scientific circles of the times. In particular, Constantine had many contacts in England and corresponded regularly with Mersenne and was friend of Descartes. Tutored at home by private teachers until he was 16 years old, Christian learned geometry, how to make mechanical models, and social skills such as playing the lute. His mathematical education was clearly influenced by Descartes, who was an occasional visitor at the Huygens home and took a great interest in the mathematical progress of the young Christian. In 1656, he patented the first pendulum clock, which greatly increased the accuracy of time measurement. His work on the pendulum was related to the other mathematical work which he had been doing on the cycloid as the result of the challenge by Pascal. He also worked on improving lens or spring-regulated clock on pendulum clock. He also formulated the inverse square law of gravitational. He also showed the fallacy in methods proposed by Gregory of St. Vincini, who had claimed to have squared the circle. In the final years of his life, Huygens composed one of the earliest discussions of extraterrestrial life, published after his death at the Cosmoteros, 1968. Sir Isaac Newton in 1643 and 1727.
Sir Isaac Newton. He was a scientist, mathematician, an astronomer. He was born on January 4, 1643, in Woolsthorpe, England. His father's name was Isaac Newton Sr., and mother's name was Hannah Ayscough. His father was a farmer and had died 3 months before Newton's birth. His mother remarried when Isaac was 3 years old and left young Isaac in the care of his grandparents. Isaac attended school, where he was an adequate student. At one point, his mother tried to take him out of school so he could help on the farm, but Isaac had no interest in becoming a farmer and was soon back at school. Newton attained his preliminary education from the King's School in Grantham, where he excelled and achieved the top rank. He then enrolled himself as a sizar at the Trinity College, Cambridge, in 1661. The young Isaac Newton is sitting in his garden when an apple falls on his head, and, in a stroke of brilliant insight, he suddenly comes up with his theory of gravity. He would spend much of his life at Cambridge, becoming a professor of mathematics and a fellow of the Royal Society. He eventually was elected to represent Cambridge University as a Member of Parliament. Isaac had to leave Cambridge from 1665 to 1667 because of the Great Plague. He spent these 2 years in study and isolation at his home in Woolsthorpe, developing his theories on calculus, gravity, and the laws of motion. In 1696, Newton became the Warden of the Royal Mint in London. He took his duties seriously and tried to get rid of corruption as well as to reform the currency of England. He was elected President of the Royal Society in 1703 and was knighted by Queen Anne in 1705. In 1687, Newton published his most important work, called the Philosophiae Naturalis Principia Mathematica. In this work, he described the 3 laws of motion as well as the law of universal gravity. Newton invented a whole new type of mathematics, which he called fluxions. Today we call this math calculus, and it is an important type of math used in advanced engineering and science. He died at March 31, 1727, in London, England, at the age of 84. To every action, there is always opposed an equal reaction, said Isaac Newton.
Here are some contributions of Sir Isaac Newton. He laid the foundation for differential and integral calculus. He also learned that the integration of the function is merely the inverse procedure to differentiating it. At the same time, Leibniz was discovering it. He also produced simple analytical methods that unified many separate techniques previously developed to solve apparently unrelated problems such as finding areas, tangent, the lengths of the curves, and the maxima and minima of functions.
Newton chose not to publish his revolutionary mathematics straight away, worried about being ridiculed for his unconventional ideas, and contented himself with circulating his thoughts among friends.
Despite being by far his best-known contribution to mathematics, calculus was by no means Newton's only contribution. He is credited with the generalized binomial theorem, which described algebraic expression with 2 terms such as
That was Gottfried von Leibniz, most prolific philosopher of all time, inventor of calculus, and the last universal genius. Hopefully then it goes without saying that any attempts to give a comprehensive summary of the works and ideas of Leibniz cannot be accomplished in a single video. He was called a universal genius because he made so many widespread contributions to so many different disciplines. Therefore, instead of attempting to do that, we will touch on some influential elements of his work in mathematics and his work in philosophy. Specifically, we're going to touch on his contributions to calculus and that debate, and his ideas about modality and religion. But first, we're going to take a look at his life, very briefly. Leibniz was born in 1645 in Leipzig. Leibniz's father was a professor at the University of Leipzig, and his son had free range of his father's library while growing up, which gave him access to texts that most people would not have had access to until attending an official university. He entered his father's university at the age of 15. By the age of 16, he had graduated with a bachelor's degree in philosophy. At the age of 18, he was awarded a master's degree. He was given a bachelor's degree in law after 1 year of study at age 19. That same year, he published his first book. At age 20, he earned a doctorate in law, as well as his license to practice law at a different university, because his father's university would not accept him into the doctoral program because he was too young. For most of his life, Leibniz made a living in law, politics, and international diplomacy. He did fall out of favor in his later life due in large part to the dispute between Leibniz and Isaac Newton regarding who invented calculus. Now, around the same time, both Leibniz and Newton claimed to have invented calculus. They accused each other back and forth of plagiarism, and there was a whole dispute about who made up calculus first. Generally, today, we consider them both as independent inventors of calculus, and there are arguments one way or the other. The notation that we use today for calculus can be credited to Leibniz. However, at the time, it was a heated debate,
the
and
basic
it led
features
to him
of his
falling
version
out
of
favor
calculus.
with many
That's
people.
what he said in
Due
his
to this
speech.
and other disputes
He
near the end
wrote
of his life,
a
very
manuscript
few
using
notable
the
thinkers and politicians attended his funeral,
JFX
even though, as noted
notation
before, he kept
and the
correspondence
product rule
with thousands
for
of people.
differentiation
And
for
his
the
grave
first
was
time
left
on
unmarked for many
21st of
years.
November 1675. After all, he had many other interests such as philosophy. Ultimately, his works at the Royal Mint. However, in 1684, the German Leibniz published his own independent version of the theory, whereas Newton published nothing on the subject until 1692. Published details of his differential calculus, including the familiar denotation, the rules for computing the derivatives of power, products, and quotients. He also perfected the binary system of arithmetic sometimes around 1617. Although the Royal Society, after due deliberation, gave credit for the first discovery of calculus to Newton, and also give credit for the first publication to Leibniz. Something of the scandal arose when it was made public that the Royal Society's subsequent accusation of plagiarism against Leibniz was actually authored by none other Newton himself. An ongoing controversy which marred the career of both men. Like Newton, Leibniz is also a member of the Royal Society. Thank you for listening and watching our video.